Hi, welcome to a lecture on physics-informed neural networks. In this lecture, we will first learn about what exactly is PINN, famously also known as physics-informed neural networks, and then finally we will implement it in Python. So let us think about what neural networks do. Neural networks can learn any kind of data, even if the data is produced as a result of running a very complex function. And because of this, neural networks are also famously called as universal function approximators. And there is even a theorem which we have covered in a lot of detail in our channel called as universal approximation theorem, which says that a neural network with just a single hidden layer and finite number of nodes in the hidden layer can learn pretty much any continuous function within a given range of input values. So, but the problem with this is that although neural networks can approximate any function, it's not always a good thing, because just like how it can approximate your signal, it can also approximate noise. So if your data set has a lot of noise, or if it has a lot of outliers, neural network is also good at learning that. So this can lead to something like overfitting, which is definitely not a feature of neural network. It's like a bug. So we will learn about how physics-informed neural network can help you make a better model by combining physical knowledge about a system. For this, we will imagine a hypothetical experiment. Let's say you are conducting an experiment by throwing a ball. The ball is thrown either at an angle, or it can be also thrown right vertically up and it can come down. But basically what you're doing in the experiment is you are measuring the height of the ball at different points of time. And when you take your measurements and when you plot the height which you measured as a function of time, you might end up with a graph which could look like this. Its shape can be somewhat like a parabola. So here, this graph shows that you have done a total of 1, 2, 3, 4, 5, 6, 7 experiments, and you have measured the height of the ball at 7 discrete time points. And now you have a kind of a function which correlates your time to height. Although this is experimental. It is very much possible to train a neural network using just this data set, so that you can predict the height of the ball even at those time points where you did not perform an experiment. Meaning, even for this time point where you don't have any data available, you can train a neural network to make a sensible prediction, something like this. So this is what traditionally neural networks do, right? So they train on the training data. And when you want to test the neural network, you expose to unseen data. So you expose, in this case, the neural network to time points which are not part of your experimental data set. So before going into that, let's quickly discuss how this training is done. So let's think about training a regular neural network. We are still not talking about physics-informed neural networks, just a normal feed-forward neural network. So here, the input is obviously time, and the output is the height, and height is a function of time. So you just have one input and have one output. In between, you could have hidden layers of whatever size you want. Here I have drawn just 2 hidden layers with 2 nodes each. You can have few or large number of hidden layers, no problem. But the input T is provided to the neural network to make it predict a predicted value of height. Now, you know that neural networks are usually initialized with random weights, meaning the parameters of these individual nodes, the connections between these nodes, these are called weights. So this is weight W11, W12, this could be W21, W22, this could be W23, W24. So you have all these weights. Here also there will be weights and there will be activation function. But the values of these weights, and sometimes if biases are also present, which are all parameters which define your neural network, they are initialized randomly. And what that means is, for random weights, the prediction also will be random. Even if you provide input T as this number, whatever this is, let's say this is T0 and T1. Even for T0, the neural network will make a random prediction. So let's say the neural network is making predictions as shown in this graph, where these yellow dots correspond to predictions made by the neural network, and these blue circles correspond to your actual experimental data, which you just saw above. Now, clearly, you can see from this data that neural network is not good because there is something called as error. So there is a difference between what is being predicted by the neural network and what is the reality. So there is this much difference, this much error for these data points, right? So predictions are very much far off from reality. So you have to communicate this to your neural network, right? Which means you have to kind of penalize the neural network for predicting far away from your experimental data set. So, and only then you can communicate to the neural network that, hey, your parameters are not good. You have to adjust it in a certain way so that you can make better predictions. So how do you communicate this to the neural network that the predictions are bad? This is done in the form of something called as loss functions. So loss function is what we will be looking at next. A loss function is simply a measure of how bad the predictions are of a neural network or any ML model compared to the real data. And how is the badness quantified here? By looking at the distance between, by looking at the gap between the predicted data and the real data, right? And here there are 7 data points for which this error is happening. There is an error in the prediction. So how can we quantify the net loss? So there are 3 options which we can think of. In the first case, here I'm defining loss as average of, so sigma I equal to 1 to n. So here it will be I equal to 1 to 7, yi minus yi cap. So yi means the actual data. In our case, it is height. So it is hi or h of ti. And yi cap is the height predicted by the neural network of what the height of the ball should be at the time point ti. Now you take the difference between them and you average it. This could be a loss. And the problem, however, with this loss is that look at yi minus yi cap. It's just a parameter which has some sign. This can be positive or negative. So if your real value is greater than so if real value blue, so this is yi. All these guys are yi cap. And all these guys are yi, experimental data. So whenever experimental data, blue circles are above the yellow circles, you have a positive error. Otherwise, you have a negative error. So now think about what's happening here. Here, positive errors and negative errors will cancel each other. For this data point, you have a negative error. For this data point, you have positive error. Here it is positive. Here it is negative, positive, negative, positive. So bunch of these positive and negative error pairs can simply cancel each other, reducing the overall loss. So you might even think that sometimes the loss can be 0 also, right? Because what if there was one more data point so that it's even number and all these positive and negative errors are canceling each other. That means the loss can be like 0 also, but you know that this is not a good neural network because individual predictions are bad. So that is one reason why this is not a good loss function. So then we can think of, okay, let's keep absolute value in that case. Then the error is always positive. Error is the difference between the real value versus minus the predicted value, absolute value. This is fine, right? This is okay. But the only problem is that an absolute value function, think about y equal to modulus of x. This absolute value function is continuous and differentiable at all points except at x equal to 0. So this is the shape of y equal to modulus of x. And the problem with this is when we ask the neural network to modify its parameters called as weights, we do it using something called as gradient descent. So new parameters of the neural networks equal to old parameters, the previous parameters minus eta, which is the learning rate, times dou by dou parameters. So whatever is the current parameters, whatever is the parameter which influences the loss, you are differentiating the loss with respect to the parameters. So which means the loss function, whatever this is, and loss is a function of parameters because the loss depends on what parameters you use in the neural network, meaning the weights, biases, etc. So the loss function, ideally you want it to be differentiable, but if you use an absolute value function, it is not differentiable at x equal to 0. So this is also not ideal. That is why people came up with a better loss function called as mean squared error, where instead of absolute value, you take the square of this so that all these individual error terms will be positive. And also this will be like a square function which is differentiable at all the places. So shape of a graph which looks like y equal to x square. So if this is x and if y equal to x square, it will be like this. It is continuous and it's differentiable at all places. So this is called mean squared error because this is error. Yi minus yi cap is the error. Squared because you are taking the square of it. Mean because you are dividing, you are summing up all these individual error terms, square of individual error terms, and you are dividing it by the number of data points, 1 by n. So this here, it should be ideally capital N, not small n, because here you're dividing by capital N, right? So this is the mean squared error, which is very famous. So option one, which was simply taking the difference error with its sign, this is not good because positive and negative errors will cancel each other. Option two is not good because in absolute value terms, I mean, if we take the error in absolute value, the function itself, loss function itself, can become non-differentiable. Option three, which is mean squared error, MSE, this is the best. So here, mean squared error tells you now the degree of how good your neural network is. Because if mean squared error is very small, your neural network predictions, which are these yellow dots, will fall very much on top of the experimental data. So they will overlap each other very, very well. So if a neural network makes predictions like this, then in that case, you are having a very good neural network on the training data. Testing, we are yet to see. But here is the issue with this approach, right? If your experimental data was not good, what happens? So just look at this image here. I measured some height of this thrown ball as a function of time. Overall, my experiments are okay, but there is one data point which stands out almost like an outlier. This might have happened because of various reasons. Maybe I did not perform my experiments well. I was like a sloppy experimentalist. Maybe the sensor that I was using, perhaps it had some issue. When I was measuring at this time point, it had some issue, and that issue resulted in my height measurement to be bad. Or maybe there was a sudden gush of wind which caused the ball to erratically move. Who knows, right? Many things can happen. So in reality, whenever you have real life data, it will have problems like outliers. It can have noise. It is never according to what you can predict using simple equations. So now if you are training a neural network on this data and you are trying to reduce or minimize the mean squared error, what will happen? This is what will happen, because if you are now training a neural network on this data, neural network can learn that also. So now the mean squared error is again 0 here, and you see the predictions are really good. So in both of these cases, so look at these two graphs. Here also mean squared error is very small, close to 0. Here also mean squared error is very close to 0. But tell me, which one is better? Which neural network is better? You might be tempted to say that this neural network is better. Why? Because here the neural network is also not just learning the pattern in the data, it's also learning issues in the data, because this outlier is an issue and the neural network is also learning that. So this is a problem. So in this example that we are talking about, right, this phenomenon you could call as overfitting, like fitting an outlier, overfitting because you are finding patterns in the data, plus you are also finding noise or outliers in the data, and your neural network is modeling all of that, which is not necessarily good. So this is where you can bring physics into the picture. Basically, when you throw a ball at an angle or directly vertically up, you know the behavior of this ball beforehand. You can predict some of that based on Newton's laws of motion. So you have gravity acting downward. You may have some force of air drag. You may have some wind. You may have a little bit of buoyancy. But maybe you can ignore all of that, and still with a decent degree of accuracy, you can make a prediction on the trajectory of the ball. So if you were to plot based on physics, so you know that S equal to ut minus half gt square. So here u is the initial velocity. So so this is the equation, right? Sorry, this is the equation. Where you have the displacement equal to initial displacement plus whatever is happening. So if you are only interested in how high the ball is going from your initial location at time t equal to 0, your displacement is s0 plus whatever motion happened due to you throwing the ball. So this is, that this is approximately how you can describe the height of the ball. So that also can give you a parabolic shape like this. But please note that your physics probably will not be in perfect alignment with what you observe experimentally. There can be issues in the experiment leading to data set being a little bit incongruent with the experiments, or maybe your physics model is too simplistic where it is not accounting for drag or other forces which may be acting on the ball. Here you are saying that the only thing that is acting on the ball is gravity. And even there, you might be making a lot of assumptions about the acceleration due to gravity, or there are many assumptions that go into making a simple model like this. But however, still that your experiments probably will not deviate too much from this known physics. And for that reason, that since this data point is too far away from this dotted parabola, which describes the Newtonian physics, that something is wrong with this experiment. And that if you were to model a neural network, it ideally should not allow to make predictions far away from this dotted line, because this dotted line corresponds to physics. And if you make predictions too far away from physics, then essentially you are violating something, right? So somehow it will be very, very good if neural network can not deviate too much from what the physics says, meaning you somehow penalize the neural network whenever it makes a prediction too far away from this dotted line. So let's see how to do that. And the question is, how do you teach physics to neural network? So let's think about this. How does neural network communicate, or how can you communicate to the neural network that your prediction is bad? You can communicate that in the form of loss function, which means if you want to make predictions closer to the dotted line, somehow that has to be incorporated in the loss function, because loss function finally tells the neural network that, hey, your loss is very high, and these weights are contributing positively to the loss by this much. These weights are contributing negatively to the loss. So adjust the weights positively or negatively such that the loss can be decreased. This is, in essence, gradient descent. So you have to modify the loss function such that the loss is high when your predictions are far away from this dotted parabola describing the physics. And the loss is probably not that high when neural network makes sensible predictions like closer to the dotted parabola. And this is where we enter physics-informed neural networks. So PINN, called physics-informed neural network. The goal of PINN is to solve differential equations by embedding the dynamics described by physics, which you will see in the form of differential equation. So in this ball throwing example, we will see how to do this. But basically, you should embed this in the training objective of neural network, which is loss function. So the objective of neural network is to minimize loss function. So if you can embed the physics somehow in the loss function, you are training the neural network to respect physics. So the idea of PINN was for one of the first times introduced in this seminal paper called by Mazia Rasi. So this is their GitHub page, the GitHub website page. It's an amazing paper. If I remember correctly, it is cited more than 5,000 times. There are other papers also which came. And this was a highly celebrated paper, and it has also like a famous GitHub repository associated with it. Let's check. So this is the GitHub repo. It has 4,300 stars, very popular GitHub repo. And the website which I showed you is already linked in the repo. So I recommend you to just go through the paper, but I will also explain you how exactly the physics-informed neural network works. The basic idea is you should not train the neural network only on the experimental data set, which I showed you as those blue dots, not the dotted parabola, but the initial experimental data. But you have to have a loss term or data mismatch term, meaning whenever you stray too much away from the data, that should contribute to loss. But whenever you stray too much away from your physics described by differential equations and also described by initial or boundary conditions, so whenever your predictions are straying away from what the differential equation predicts, or what the initial or boundary condition says, that should also contribute to a loss. If your loss can be modified like this, then indirectly you are asking the neural network to learn the inherent physics in this phenomenon. So in our example of ball throwing, let us implement physics-informed neural network. So firstly, let us look at what is the differential equation that governs the motion of a ball. It is velocity equal to u minus gt. And velocity in our case can be described by rate of change of height. So dh by dt is equal to u naught minus gt. And what is u naught? This is the initial velocity with which you are throwing. Here, just imagine for simplicity that you are throwing vertically up. Otherwise, you have to have components for height as well as horizontal movement. So just for simplicity, assume that this is the velocity in the upward direction. So dh by dt equal to u naught minus gt is the differential equation that governs the motion of a ball. However, this ODE, this ordinary differential equation, cannot fully describe our system because height cannot be fully determined, meaning uniquely determined just with the help of this differential equation. You also need an initial condition. So you can think of it mathematically. So mathematically, this is a first order differential equation, ordinary differential equation, which means if it is in time, you need one initial condition. If it was in space, you would need at least one boundary condition, right? So here you need one boundary condition, which will be, since you are trying to predict height, sorry, not boundary condition, initial condition, which will be the initial height when you started to throw. So that is the initial condition. What was the height when time was equal to 0? But logically also, there is one way to think about this. So let's say there are two people. This guy is throwing from a height of 5 meters. This guy is throwing from a height of 10 meters. So this guy is standing on a, let's say, taller platform. I'll just elongate this perhaps. Maybe that way confusion is not there. Like this. So the guy behind is throwing from a bigger platform of height 10 meter. This guy from a 5-meter platform. So the velocity in both of these cases will look exactly the same because dh by dt depends on dh by dt equal to u0 minus gt. So as long as u0 is the same and as long as the starting point of your throw is the same, dh by dt will be exactly the same, but still it does not uniquely determine what is h of t, because in this case the height is higher, like this is taller always. This parabola is always taller than this parabola because the starting point is different. So this is why you also need initial condition logically in this particular case to describe fully what your h of t will be. So now let's think about what the neural network should do. It is not just enough for the neural network to make predictions, accurate predictions on dh by dt, but we also want the neural network to make accurate predictions on the h of t at t equal to 0, meaning the initial condition. So we want the neural network to make predictions that are closer to the data set. We want the neural network to make predictions such that a predicted value of dh by dt, which we will come to in a moment, should be same as the actual value of dh by dt described by the ordinary differential equation. And not only that, we also want a predicted value of initial condition provided by the neural network to be very close to the actual initial condition, which is h of t equal to 0, whatever was the initial height, right? So now how do we describe the loss function due to ordinary differential equation? So we mentioned three losses: loss due to data, loss due to ordinary differential equation, and loss due to initial condition. So think about what the neural network is predicting. In our case, the neural network is predicting height. It is not predicting dh by dt. You provide an input time and it predicts height. So then how do you define a loss due to dh by dt? Of course, we know the Newtonian dh by dt. It's simply dh by dt equal to u minus gt. However, what is this? What is this dh by dt predicted by the neural network? Isn't neural network predicting h? How can you get dh by dt? The answer is a concept called automatic differentiation. So basically, for most of the popular frameworks like TensorFlow, PyTorch, JAX, for all of these frameworks, there is there are packages available for performing automatic differentiation, where you can differentiate the neural network itself, and that will help you predict not only the h but also dh by dt if you are differentiating with respect to time. So you can have a dh cap by dt. So previously we said that you have h cap, which is the predicted height, and h, which is the actual height. But now you can also have dh cap by dt, which is the derivative of the predicted height, and that you obtain by taking the derivative of the neural network itself. And you have the actual dh by dt described by the Newtonian mechanics. This is the physics-based dh by dt. Now you can describe a difference between the predicted dh by dt and actual dh by dt in this following, which I prefer to call as ordinary differential equation loss, ODE loss, because it can be described as 1 by n sigma equal to 1 to n dh by dt what, dh by dt at time t equal to ti minus dh cap by dt at time t equal to ti. And we know dh by dt equation. Dh by dt is simply, according to Newtonian mechanics, it's simply u0 minus gt. So if it is dh by dt at time ti, then this will be simply ti. That's all. So that is this term u0 minus gti. And dh cap by dt is the derivative of the neural network at time t equal to ti, the whole square by n. So you are summing the error of these derivative terms. You are squaring them. You are summing the squares and you are dividing by n. So it's like a mean squared error, but you're not calculating the mean squared error for h and h cap. We are calculating the mean squared error for dh by dt and dh cap by dt. So let's call this as ODE loss, because this is the loss happening in the ordinary differential equation term. Now let's look at the next loss term. Next loss term is nothing but the initial condition loss. Okay, so I have written here loss due to dh by dt. That is not the case. This should be loss due to initial condition. So what is this? This is fairly easy compared to ODE loss. Basically, the neural network is already making predictions on height. So let the neural network make a prediction on the height at time t equal to 0. That is this guy, this term, h cap of 0 or h cap of time t equal to 0. And you know the actual value of height at time t equal to 0. This may be 5 meter. This may be maybe 0 meter if the projectile is starting from the ground. So you can have a IC loss, meaning initial condition loss, which is the difference between the actual initial condition and the predicted initial condition, and you square it. In some problems, you may have higher order differential equations with spatial derivatives, which means along with the initial condition, you may also have boundary conditions. In that case also, you make the neural network predict a boundary condition, and then you compare it with the actual boundary condition and square it to define a boundary condition loss. This is an initial condition loss. Now, here is the question. Are these two losses enough? Is that it? Do we just need the ODE loss and initial condition loss? No, because we can't throw the experimental data in the basket, because we can't say that all this precious data which we got by measuring the height of the ball as a function of time, it's useless. We can't do that. So we have three things to consider, as I mentioned earlier. Firstly, you should not throw away the experimental data. Somehow the neural network should be trained on experimental data. You cannot neglect the physics described by the ordinary differential equation or partial differential equations in some other cases. You also cannot neglect initial or boundary condition. Your model has to respect initial or boundary conditions. So this is why you need three loss terms. One is the data-based, meaning experimental data-based mean squared error loss, along with ODE loss and initial condition loss. So let's look at how we can write the loss. And obviously, this should be net loss or combined loss, something like that. So now the combined loss will be the sum of three terms. Loss due to data. Loss due to data meaning how much ever loss the neural network is having when it makes a prediction. When you compare the prediction with the actual experimental data, that is the first term. Second term is loss due to ODE. So how far away your dh by dt predictions are from the reality. Third term is loss due to initial condition, IC. how far away your initial condition prediction is compared to actual initial condition. And you are noticing probably this term, lambda 1, lambda 2, and lambda 3. They are nothing but like a weight factor. Basically, it describes how much you are looking at lost data compared to data loss compared to ODE loss. So let's say lambda 2 and lambda 3 were 0, which means you are completely ignoring the physics. You only have then this term when lambda 2 and lambda 3 are 0, which means your net loss will simply become the loss due to just the experimental data. So if you are so unsure about the physics, if you have no idea what is the physics in this system, you can simply set lambda 2 and lambda 3 to be 0. On the other extreme, if you are so sure about the physics, if you say that no, only gravity is happening, there is no air, there is no wind, there are no other forces, the ball is thrown at exactly u0, the gravitational force is 10 meter per second square, I mean the acceleration due to gravity. If you are so sure about your knowledge of physics, then you can set lambda 1 to be 0, meaning you don't need the experimental data anymore because you perfectly know your system. In that case, what becomes the loss term becomes these two things, ODE loss and initial condition loss. And essentially then it will become like you are solving a differential equation, because when you minimize the loss, your neural network will perfectly align with the Newtonian physics. So, but in reality, what happens is you will not neglect either of these terms completely. You will define lambda 1, lambda 2, and lambda 3 such that there is some weightage. Maybe you can give 90% weightage to experimental data and 10% weightage to the remaining two terms. You could do vice versa. You can give 10% weightage to the experimental data and 90% weightage to the remaining terms by adjusting the value of lambda 1, lambda 2, or lambda 3. And this is very much similar to hyperparameter tuning. You can't know in advance what is a good value of lambda. A good value of lambda depends on your knowledge of the knowledge of your system. It depends on how reliable your experimental data is, etc. And what is your goal? Your goal, if all these three terms are present, what you are saying is, I have some experimental data and I don't want my predictions to go far away from the experimental data. I don't want my predictions to be so far away from experimental data. That is what the first term will ensure, this first loss term. The second and third loss term will ensure that the predictions are not too far away from this dotted purple parabola, because that is the Newtonian physics. So the loss will be very high if a prediction is somewhere here. This data point is so far away from the experimental data, it's also so far away from the parabola. So the loss of this point, which will be introduced in these three terms. For the first term, very high loss will be there. For this term, also very high loss will be there. How about making a prediction? So for at this time t, how about making a prediction here? If it makes a prediction here, then you are perfectly predicting physics, which means the loss due to these two terms, due to the second and third term, will be low, but you are making a prediction far away from your experimental data. So in that case, there will be a huge loss contributed by this. What if your prediction over here was here? What if you made this prediction? It means the contribution to the loss due to this term will be negligible, but you will have a huge loss because you are now predicting far away from your parabola. So that is why if you have all these three terms, maybe you will predict neither too far away from your experiment nor too far away from your physics. Maybe you will make a prediction something like this. Whereas if you did not have physics, you would have minimized the loss and you would have made a prediction where you are too much leaning towards the outlier. But now you kind of minimize or diminish the effect of outlier so much. So this is the power of physics-informed neural networks. So the data loss term ensures that you are not far away from experimental data. OD loss plus initial condition ensures that you are not too far away from physics. And if you are pretty sure about the physics, you can set the first error term's coefficient lambda 1 to be 0. If you are not sure, meaning, you will be sure if only gravity is present. But if you are not so sure, you will have lambda 1 plus other lambda terms in your net loss term. This is when you have true PINN. Now, where is the informing part happening? PINN stands for physics informed neural networks. Basically, you are informing the neural network that some physics is present behind this data. And how are you informing it? Through loss function. Because if loss function value is very high, neural network will have a tendency to adjust its weights in such a direction as to minimize the loss. So it's a very simple concept, but it really blows my mind that with just such a small, simple tweak, you can embed so much of information about physics into neural networks. So I absolutely love this concept. Now what we can do is we can perform a Python implementation where this exact same problem of throwing a ball up in the air and coming down. Let's see what kind of predictions can a traditional neural network make and what kind of predictions can a physics-informed neural network make. So I have already written the code. I have already tested it. It's working beautifully. But instead of directly running it on Google Colab, I will do it eventually. But I first want you to go through the blocks of code, the meaningful blocks of code. So we'll be using PyTorch. So we implement the torch modules. NumPy we are importing, torch we are importing, and matplotlib for plotting the graph of the trajectory of the ball, predicted trajectory, experimental trajectory, and PINN predicted trajectory. So this is the pretty simple code block. In the second code block, what we are doing is we'll be generating synthetic data to kind of mimic an experimental data. We can also add some noise so that the data does not look like a perfect parabola. So here, some parameters we need to define, right? So acceleration due to gravity, 9.8 or 10 meter per second square. Initial height, we will say it's 1 meter. Maybe when you are throwing something up, if a person has 1.8 meters height, maybe the ball is starting from 1 meter height, something like that. And initial velocity, we can say it's 10 meter per second. So we know that the solution is height as a function of time is the initial height plus h is equal to u initial height plus ut minus half gt square, where this u is the initial velocity. So we can, if we provide time as an input using this equation, we can get height at any given point of time, right? And initial height is 1 meter, initial velocity is 10 meter per second. So this function basically creates the ideal data set without any noise. Then we can say, okay, we are going to generate data points from times t equal to 0 to t equal to 2. And we need 10 data points. So number of data points is 10. And we create a grid of data points, time data points, where you have 10 data points spread between 0 second and 2 seconds. So that is this linspace. Now we have a random seed to have a repeatable neural network output, because neural network is initialized with random weights. But when you have a seed, as long as the seed is the same, you can get repeatable output. And this noise level is a number that defines how much you are going to perturb this data set returned by the true solution to have something that mimics the experimental data. I will show the graph, then you will understand how this noise is impacting the data. But basically, instead of having data nicely distributed over a parabola, you may have data points like distributed slightly like this, because you are adding a noise on top of the data generated using the equation of a parabola. So the exact solution data is obtained by calling the true solution function. This is the true solution function for your time points, and time points is the linspace of this t data, right? Noisy is basically the exact data plus some noise level, and this noise level is 0.7, and 0.7 you are multiplying with a set of random numbers. So the height of this noise won't be same. It will depend on whatever this random number generator is generating. Then you have the time data converted into a tensor, and height data corresponding to time data converted into a tensor. So now what you are going to train your neural network is to train such that this is the input tensor and it is supposed to predict this at the output. This is what it's supposed to predict. This is what it is, what is the input, and this is what it's supposed to predict, right? So you are converting using PyTorch tensors, you are converting the time data and height data into tensor. Now, we need an automatic differentiator, because if you want physics-informed neural network, you need dh by dt, and you also need dh cap by dt, where this is obtained by the automatic differentiation. This you already know from your equation, from your Newtonian physics. So here, there is the automatic differentiator, PyTorch autograd. Maybe it stands for auto gradient, automatic gradient. But basically, you can differentiate a neural network at any given point of h and t. And you can think of it in one way. So for example, let's say a neural network is making predictions of height. So let's say this is h cap as a function of time. One prediction is here, one prediction is here, another is here, another is here, another is here, and another is here. So now if you want, okay, the predictions are of h, but you can find dh by dt from this. Let's say you were able to find quickly the slope of this line, then you can approximate that line's slope to be the dh by dt at this point. If you know the slope of this line, then that could be the dh by dt at this point. Similarly, so like this, it's very much possible for the neural network to provide you indirectly a dh by dt. And automatic differentiation function makes this whole process of calculating dh by dt at any given point much more easier, right? So that is what we are returning here, the outputs of the automatic differentiator, and that is wrapped inside this function called derivative of y comma x. Now, for PINN, we need to define a loss, although we are going to run PINN as well as a normal neural network without physics-informed neural network. And we'll see how the outputs differ. But basically, there are three losses we discuss. One is the data loss due to experimental data. What is experimental data? In this case, it is the noisy data. We created the parabolic data plus added noise on top of it. So that is the first set. Second is ODE loss. ODE loss is nothing but dh by dt minus dh cap by dt. Third is initial condition loss. So these three we need. So there are three functions also: physics loss function, initial condition loss function, and data loss. So data loss is the function which you normally need. If you don't have a physics informed neural network, you only need this function. But otherwise, you need a physics loss for dh by dt loss and initial condition loss for initial h of 0 loss. So here what we are doing is, first, we make the model predict, we make our neural network model predict a height for a given value of t. Then for that value of t plus the predicted height, which is y, is passed into this derivative function. And what is this derivative function? This guy. Derivative function is the automatic differentiation function, and it will return, this will be dh by dt predicted, basically dh cap by dt. That is stored in this variable. Now you will calculate the true dh by dt, which is v minus gt. This you know from physics. Then the loss will be basically a mean, squared mean of the difference between dh by dt predicted and dh by dt true. That is this, dh by dt predicted minus dh by dt true raised to 2. So that is the ODE loss, and then this function returns the ODE loss. Similarly, initial condition loss is very easy. Initial condition loss is firstly, when time t equal to t naught, what is the model's prediction? That is h naught predicted minus the initial value h0. H0 is nothing but the height at time t equal to 0, or time t equal to the first data point in your height values. So h naught predicted minus h0. And that will be returned by the initial condition loss function. And finally, the database loss is how far your predictions are from your experimental data. So this is simply mean squared error between your predicted height, which is h cap, and the data which you have from your noisy data set raised to 2, and you take the mean. So that is returned by the data loss function. Fairly easy. Now the training setup. So we first define the optimizer. Optimizer means when you are performing the gradient descent, what kind of gradient descent are you doing? Are you doing a vanilla gradient descent, or are you doing stochastic gradient descent, or are you doing momentum based gradient descent? No, in this case, we'll be using Adam optimization with learning rate to be 0.01, meaning theta new equal to theta old. Theta is the model parameter minus eta times gradient of loss, right? So now this eta is 0.01. That is what this means. And okay, here comes lambda. So lambda data means the you have three loss terms, right? Lambda 1 times loss due to data plus lambda 2 times loss due to ODE plus lambda 3 times loss due to initial condition. So here lambda data is 1. This is 1. This is also supposed to be 1 because I wanted all the terms to be there. So let's keep this 1.0. And the last one is lambda 3, which is lambda IC, initial condition lambda. Number of epochs is the number of iterations for which you are running this forward propagation and then gradient descent. So 2000. And then we'll be printing once in every 200 iterations, right? And after this is done, now we can call the training loop. So for epoch, in range of number of epochs, we have optimizer, then we have loss function called. So data loss is the loss due to data. Then physics loss is the loss due to physics. Initial condition loss is loss due to initial condition. And look at what are we passing here. In the data loss, we are passing the model We are passing the tensor in which we are storing the time data. We are also passing the h, the tensor in which we are storing the height data, because in data loss we will be comparing whatever model's prediction is of the h and whatever is stored in this tensor. In physics loss, we will look at whatever the model's prediction is for the dh by dt, and you don't need the height data because height data is calculated using u minus gt, that formula. Sorry, dh by dt will be u minus gt, yeah, u naught minus gt. And for initial condition loss, you don't even need the time data tensor, because it's predicted by the models. So it's the difference between models prediction for the first time point and the initial condition itself. So let's see in the initial condition function, where are we mentioning the h naught? So at time t equal to 0, t naught is this. H naught predicted is model of t naught. That is the predicted one. And h naught is, I'm just trying to figure out where is this h naught defined. I think it's defined somewhere. Okay, h naught is defined here, the initial height. Okay, so we don't need to pass anything because initial condition is already available as a global variable. Yeah, so that is the training. Calling the loss functions individually. Then the combined loss is lambda 1 times loss due to data, lambda 2 times loss due to ODE, and lambda 3 times loss due to initial condition. And then we perform, so once the loss is calculated, we perform backward propagation using the optimizer as Adam. And then if the epoch is once in every 200 epochs, we will print the total loss, data loss, ODE loss, initial condition loss, and also the epoch number. So this we'll be printing. So once the model is trained, now we can see by plotting how good the model has made the predictions, right? So first we need a x-axis. X-axis will be time. Then we need the y-axis, and we should have three type of data on the y-axis. One is the data without PINN. One is, predictions without PINN. One is predictions with PINN, and one is the noisy data itself. We can also plot exact solutions. So in this case, actually, we are only plotting 1, 2, 3 things. Noisy data, which is the actual exact solution plus noise, exact solution itself, which will be a parabola, and PINN prediction as the third plot. So now we can copy paste all of this code into the Google Colab, which I have already done. So this is our Google Colab notebook in which all the code is already pasted. Now let us just run this. So first block is about importing the data set, then generating the noisy, good data plus noisy data. Then the third block is feed forward neural network definition with the number of hidden layers. Then here we are also mentioning that the number of hidden layers is 20. I don't think we discussed about this part when we discussed the structure of the code. The PINN class was defined to define the neural network structure. And in that we are sequentially adding 20 hidden layers, followed by tan hyperbolic activation function, then another set of hidden layers, activation function, and then the final layer. And let's run this. Then the derivative function acting as automatic differentiator. Then you have 3 loss components. So there are 3 functions here: physics loss, initial condition loss, and data loss. Then you have training setup. So here, let me put the lambda ODE also as 1. So all the 3 terms will be there. Data loss, ODE loss, and initial condition loss will be there. And then let's call the training loop. And here it will print the epoch number and the loss. And you can see that the loss is continuously decreasing. All the losses, in fact, initial condition loss, ODE loss, data loss, everything is decreasing. And now if you plot, see, so although your noise is very high, so the dotted black line is the exact solution. S is equal to ut plus half at square plus the initial height. That is the exact solution. And exact initial condition, you knew that height was equal to 1 initially. And you can see that initial condition is being satisfied. And it's like a parabola. However, your noisy data, which may be your experimental data set, these red dots. They are very, very, very bad, right? Experiments are very bad. Now imagine your neural network was perfectly fitting through all these red dots. It would have been very bad. You don't want that to happen, because you know that this is not conforming to physics. But so you want a neural network, you want the neural network to make a prediction which does not ignore the experiments completely, but also does not ignore the physics, and that is the blue curve, PINN prediction. Now let us do one thing. Let's say we increase the value of lambda due to ODE to 20. So now we are placing huge weightage on ODE loss and less weightage on data loss. Now let's see how much the neural network will come closer to that perfect ideal solution, right? Because of this, let's see. Because now to decrease the total loss, the neural network will have to do a really good job. Okay, it did not come that much close. Let's do the opposite. What we can do is let's keep the ODE loss, and actually one more thing, yeah, lambda due to initial condition also let's increase, and let's see how much the neural network will learn due to this. This is the new prediction. I'm not sure if the PINN solution is coming closer and closer to exact solution. Maybe it will if I change the lambda data to 0.001. How about this? The lambda, now I'm placing very less importance on the data part of the loss. Let's see what happens in this case. I don't see much improvement actually. Then let me do the reverse. I will say that I don't want ODE loss at all. It will be 0. Okay. How about this? I put the data lambda to be 0. How about now? What if this is 0, I only want PINN? What happens in this case? Maybe I have to increase the number of, now something is happening. So if I were to increase the number of iterations from this to 4,000, maybe you will have a prediction which is very, very close to the actual ideal solution. So maybe now the blue curve after the end of this set of iterations, the blue curve and now see the blue curve and this black dotted curve, they are very, very close to each other, because now my data loss is very small. Okay, how about this? I have this to be 1.0. So I want the experimental data not to be ignored. I want initial condition also not to be ignored, but I'm okay with ignoring the ordinary differential equation. What happens in this case? And I just want 2000 iterations. I don't want 4000. In this case, the neural network should probably have the initial condition same as h of 0 equal to 1. And the neural network should hopefully fit through all the data points instead of, trying to be closer to the physics, meaning trying to be closer to the ideal parabola. Let's see what happens. You see? So now the neural network is making predictions in a weird way, because here PINN is not there. Although here I have written PINN prediction is there, this is technically no PINN prediction because the ODE loss we have kept to be 0. So see, this is the problem. And now what if I did not have initial condition loss also? Then it will fit through all the points exactly, because here at least the first point, this point, there is no fit because you are forcing the initial condition on the neural network. But what if I relax that? So by putting the lambda 3 to be 0. So let's see what neural network predicts now. I hope neural network will now fit through all the data points. Yeah, you see, the neural network makes a prediction which fits through all the data points. So with a complete disregard to physics, neural network does not care about physics now. It only cares about minimizing the loss described by the experimental data. So this is the beauty of PINN, because here you know that you have an experimental data which is very, very bad. How do you know that? Because you know the physics. So if you know the physics, you embed that physics into the loss. So now you put this back to 1.0. You say that I want to respect the ordinary differential equation. I want to respect the initial condition, but I also want to respect the experimental data because it's a real world data. And now let's see what the neural network can learn. And it learns something not like this, because something is happening. Lambda data is 1.0. Perhaps I did not run the code where I adjusted the lambda. PINN prediction. Maybe the weights are not adjusting that well. So what I can do is I'll restart the session and let's see, because I think maybe the neural network is still having the memory of the previous weights because I'm running it again and again. So let's see. So now I can run all. So hopefully this will be a code without, this will be a plot without the overfitting, which we just saw. Okay, something is happening where perhaps I'm not running enough number of iterations or something. About number of epochs to be 4000 and print every, yeah, now it's running epochs till 4000 and hopefully the prediction would be better now. Something super weird is happening. This was not at all happening before. I don't know why it has saturated like this. What if this is 2.0? All of this is 2. And so basically, I want a better looking plot than what you just, okay, this is much, much better looking. Yeah. So now you have a prediction which in which you can see that the neural network is kind of trying to respect the experimental data because it's not exactly matching the solution, exact solution. The PINN solution is not matching the exact solution, but it's also not matching the noisy data. So it's kind of respecting the physics, but it's also kind of respecting the experimental data. So this is PINN. In short, I will share the code with you. Also, I will share the notes, lecture notes with you. Feel free to go through that. I really enjoy PINN because it's such a simple concept yet so powerful. I am fully aware that the problem statement which we picked is too simple, but you could pick more complex problem statements and literally apply the same concept. And so thank you so much. I really enjoyed teaching this concept, and I will be looking forward to seeing you again in another video. Take care until then. Bye.